All right, let's just dive right into it. Today in this explainer, we're really getting into the weeds of the step impulse math behind systems. We're going to look at exactly how engineers take these totally unknown mechanical mysteries and turn them into precise mathematical blueprints. And honestly, it takes just a little bit of observation and a whole lot of clever deduction.
So how exactly do you write a mathematical blueprint for a machine when you literally can't see inside of it? It's a great question, right? Think of it as the ultimate engineering detective story. We're figuring out what's happening inside a totally closed system just by, well, giving it a mathematical kick and measuring exactly how it reacts.
Here's our roadmap for today. We'll start with the black box mystery, move on to the mathematical interrogation tools, then decoding first-order systems, the second-order bounce, impulse math and time delays, and finally, building the perfect blueprint. We're going to start simple and scale up from there.
All right, Section 1, the black box mystery. This is where we meet our primary suspect in this whole investigation. Engineers affectionately call it the black box.
Take a computer hard drive, for example. It is the perfect illustration of this challenge. It's a system where we can easily control the inputs, like the motor voltage, and we can measure the outputs, like the exact position of that read-write head. But the actual internal dynamics, completely unknown to us. And without a solid mathematical model, we basically can't analyze it or design effective controllers for it at all.
Moving to Section 2, the mathematical interrogation tools. To crack this black box wide open without ever picking up a screwdriver, we're going to need some very specialized methods.
So we use standard stimuli. You can kind of think of these inputs like poking an unknown animal just to see how it reacts. A step input is basically a sustained push. It's an instantaneous change in the input that just stays there. An impulse input, on the other hand, is more like a quick slap. It's a really short, sharp, high-amplitude pulse that jolts the system for just a tiny fraction of a second.
When we record the system's output over time, we get this really cool graphical signature. We call this a transient analysis. It acts as what's known as a non-parametric model. Literally, just by observing the curve, seeing how fast it rises, if it wobbles at all, exactly where it settles, we can extract a small set of key parameters to build a super concise, incredibly accurate model.
Now, for what we call linear time invariant systems, which just means they obey the rules of superposition and their behavior scales proportionally, we can actually translate that graphical signature into a transfer function. Engineers usually write this as h of s. It's really just the mathematical ratio of the output over the input. And finding that specific transfer function, well, that's the whole point of this entire investigation.
Okay, Section 3, decoding first-order systems. This is where we examine our absolute simplest suspects so we can build up a foundational understanding.
So here is the crucial point to remember. First-order systems only have a single energy storage element. Because energy basically only has one place to build up or drain away from, their response is this entirely predictable, smooth, exponential curve. Now, second-order systems, which we're going to cover in a minute, they have two elements, which means they can actually bounce or oscillate.
The behavior of any linear first-order system, like, say, a simple thermal system warming up, is completely defined by just two parameters. First, you've got K, which is the gain. That represents the system's ultimate steady-state level. And then there's T, the time constant, which is a really precise measure of exactly how quickly the system responds.
Now, don't let the complex fractions scare you off. Let's just focus on the visual curve here. Because these systems are so incredibly predictable, we can literally just read the time constant right off the visual signature. We just have to find the exact moment the output hits 63.2% of its final value. It's literally an ironclad rule for first-order dynamics.
So by applying these three pretty straightforward steps to real-world and, let's be honest, usually very noisy data from something like a thermal heating phase, we can completely cut through the mess. We calculate the gain, we target that magic 63.2% mark on the timeline to find our time constant, and then we just plug it directly into our transfer function. It's this awesome eureka moment where we extract a perfectly clean mathematical model straight out of raw physical observation.
Moving on to Section 4, the second-order bounce. Because what happens when our system pushes back and actually starts to bounce?
When we add a second energy storage element into the mix, picture a physical mass attached to a spring, the math definitely escalates. The system can now trade energy back and forth. This means we have to solve for two totally new parameters: the natural frequency, which is basically how fast it wants to oscillate, and the absolutely crucial damping factor.
Let's talk about that damping factor, represented by the Greek letter g.
This single variable completely dictates the personality of the response. If it's exactly 0, the system violently oscillates forever. If it's under 1, it overshoots and bounces around. But if it's 1 or greater, it just cleanly settles into a steady state without ever overshooting.
And just like with the simpler systems, we don't have to blindly guess these variables. The visual curve literally hands them to us. If we carefully measure the overshoot peak, that fractional amount the peak exceeds the final value, and then we measure the oscillation period between the first two peaks, we can completely reverse engineer those complex second-order parameters.
Section 5. Impulse math and time delays. Now we're going to look at an alternative interrogation method, and honestly, a very messy reality of physical engineering.
Because out in the real world, systems just don't always react instantaneously. Things like fluid flowing through a long pipe, well, they create a lag before the output even starts to register a change. Engineers call this dead time, or time delay, represented by the Greek letter tau. All we do is measure that flat gap at the very start of our graph, and we simply multiply it right into our transfer function as this neat little exponential term.
Now, the absolute crucial point is captured perfectly right here. The impulse response is the derivative of the step response. This is a fundamental mathematical property that completely connects our two primary interrogation methods. It means all this underlying step impulse math behind systems has this profound universal truth to it. The sustained push and the quick slap, they're totally mathematically linked. When we place the step response right next to the ideal impulse responses, it reveals a much more flexible toolkit. Because of this mathematical relationship, we can develop parallel identification techniques. So instead of finding the 63.2% mark of a step input, we can just analyze the impulse curve, like finding exactly where it decays down to 36.8% of its peak. Both of these visual methods lead us to the exact same mathematical model.
Finally, Section 6, Building the Perfect Blueprint. Let's bring this all together to show you exactly why doing all this intensive math is totally worth the effort.
Finding these parameters, the gain, time constants, the damping factor, the delay, it is definitely not just some academic exercise in reading graphs. These parameters are the absolute essential foundation for predicting system behavior, running virtual simulations, and actually engineering the precise feedback control systems that allow, say, a massive robotic arm to swing into place smoothly and stop right on a dime.
The ability to create a full mathematical blueprint purely by observing a physical reaction is just a fundamental engineering skill. From the cruise control in your car to that drone hovering up in the sky, it really leaves us to wonder, if engineers can model a complex machine just by observing its reaction to a single jolt, what invisible control systems are quietly governing the technology you rely on every single day? Thanks so much for joining me on this explainer. Until next time, keep observing that invisible math shaping the systems all around us.